In this video, we're going to talk about hybridization of atomic orbitals. So what exactly is hybridization? Hybridization is basically combining atomic orbitals to make hybrid orbitals. So for example, the Sp3 hybrid orbital is a blend of one s orbital and three p orbitals. As you can see, it's s1p3. Sp2 squared is a hybrid of an s orbital and two p orbitals. Sp is a hybrid of s and one p orbital. So now you know what these terms mean. So let's say if you were to see d2 sp3, this means that you're combining two d orbitals, one s orbital, and three p orbitals. So what exactly is an s orbital? An s orbital looks like a sphere, and an orbital tells you the probability of finding an electron somewhere within the atom. Keep in mind, electrons, they can behave as particles and as waves. So an orbital simply tells you the most probable location in which you could find an electron. According to Heisenberg's uncertainty principle, we cannot know precisely the exact location of an electron. Now let's talk about the p orbital. There's one s orbital, but there's three different types of p orbitals. You can have a p orbital in the x-axis, so this is known as px. You can have a p orbital that's oriented along the y-axis, so that's called a py. And then there's one oriented about the z-axis, which we'll call pz. So there's three types of p orbitals. Now we're going to talk about the hybridization of carbon. And the electron configuration of carbon is 1s2, 2s2, 2p2. So this is the electron configuration of carbon. Now let's focus on this portion. Let's say the 2s is at an energy level here, and let's say this is 2p. I want to highlight something. So carbon has four valence electrons. Now when carbon forms an sp3 hybrid orbital, it uses all four orbitals. Keep in mind, sp3 means that we need to mix one s with three p orbitals. So where should we put the sp3 orbitals? Should we put them at the same energy level with the 2s orbital, or with the 2p orbital, or somewhere in between? And should it be like halfway closer to 2s or closer to 2p? What would you say? Now, to make an sp3 orbital, it requires four orbitals, as you can see here. So one out of those four orbitals is s, which means that the sp3 orbital has 25% s character. Now, there's three p orbitals out of four orbitals. 3 out of 4 correlates to 75%. So the 75% p character. So because the sp3 hybrid orbital has more p character than s, the energy level should be closer to 2p than it is to 2s. So it should be somewhere over here. Now all four of these sp3 hybrid orbitals, they're called degenerate orbitals. Degenerate orbitals are those that have the same energy. So these four electrons will be placed in these four sp3 hybrid orbitals. And you want to place the electrons one at a time when you're adding electrons to degenerate orbitals, or orbitals of the same energy. And that's the main idea behind Hund's rule. You want to add electrons with parallel spins one at a time, if you're adding them to orbitals of the same energy. Now let's talk about the Sp2 hybrid orbital. Let's talk about its energy first. So to make an sp2 hybrid orbital, we need one s orbital and two p orbitals. So we have three p orbitals. We're not going to use all three of them. We only need to use two. That means one of them will remain after hybridization. So the green arrow would represent the process of hybridization. So here's the unhybridized 2p orbital. It has the same energy, and now we have sp2. So one out of the three orbitals is s. So we have 33% s character. And 2 out of the 3 orbitals is p. 2 out of 3 is about 67% if you round it. So it's 67% p character. So we still have more p character than s. So therefore, the sp2 hybrid orbital should still be closer to 2p than 2s. But it should be less than sp3. So these three orbitals will have the same energy. Since we use 3 orbitals to make them, we're going to get 3 hybrid orbitals. So I'm going to put one electron in each orbital. So we should have something that looks like this. So these are the 3 sp2 hybrid orbitals. Now let's talk about the sp hybrid orbital. So after hybridization, to make the sp hybrid orbital, we need one s orbital and one p orbital. So we're going to use this s orbital and only one of the p orbitals, which means the other 2 p orbitals are unhybridized. So therefore, they will be unaffected. Now, if we have an sp orbital, one is s, one is p, 1 out of 2 is 50%. So therefore, we have 50% s character and 50% p character. So therefore, the sp hybrid orbital should be right in between the s orbital and the p orbital. And there's 2 of them. Since we use one s and one p orbital, or 2 orbitals to make the sp hybrid orbital, therefore there must be 2 hybrid orbitals. So if you were to mix 3 atomic orbitals, you should get 3 hybrid orbitals. If you mix 4 atomic orbitals, you should get 4 hybrid orbitals. We're mixing one s, one p. That's a total of 2 atomic orbitals. So that will give us 2 hybrid orbitals. And they will have the same energy. By the way, you need to know that hybrid orbitals are used to form sigma bonds. The unhybridized orbitals, in this case, the p orbitals that were unaffected, unhybridized orbitals are used to make pi bonds, which we'll talk more about later. So just keep that in mind. So pi bonds are always made from unhybridized p orbitals when you're dealing with carbon atoms. And sigma bonds, they form from the overlap of atomic orbitals, and they consist of hybrid orbitals for the most part. Every single bond that you see contains one sigma bond. Every double bond has at least one sigma, and it has one pi bond. A triple bond contains one sigma and 2 pi bonds. By the way, a triple bond is stronger than a sigma bond, or a single bond. 3 bonds are more stronger than 1 bond. It's harder to break 3 pencils than it is to break 1. So keep this in mind, triple bonds are stronger than single bonds, but triple bonds are shorter than single bonds. Single bonds are longer. But now, if you compare one bond to another, you need to know that, well, before I say it, which one do you think is stronger, a sigma bond or a pi bond? What do you think about that? Sigma bonds are stronger than pi bonds. The reason why a triple bond is stronger than a single bond is because you're comparing 3 bonds as opposed to 1. So these 2 sigma bonds, let's assume they're equal. The triple bond's going to win because it has 2 additional pi bonds. So when comparing a triple bond versus a single bond, the triple bond is stronger because you're comparing 3 bonds compared to 1. But if we compare one sigma versus a pi bond, the pi bond is weaker. It's easier to break a pi bond, but it's harder to break a sigma bond. So just keep that in mind. Sigma bonds are stronger than pi bonds. Now, let's say if you have a structure that looks like this. How many sigma bonds are in this structure, and how many pi bonds are there? So every bond contains one sigma. So 1, 2, 3, 4, 5, 6, 7. Therefore, there are 7 sigma bonds. And every double bond has one pi bond. So 1, 2 pi bonds. And that's a simple and easy way to count the number of sigma and pi bonds. So let me give you another example. How many sigma and pi bonds are in this structure? So let's count the sigma bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 sigma bonds. Now, how many pi bonds do you see? A triple bond contains 2 pi bonds. A double bond contains 1. So we have a total of 3 pi bonds. So here's the challenge problem. Determine the number of sigma and pi bonds in this structure. So feel free to pause the video and work on this example. Now what we need to do is expand the structure. So first we have a CH3, which is a carbon with 3 hydrogens. And after that comes a CH2, which is a carbon with 2 hydrogens. And that carbon is connected to another carbon, which has a double bond to an oxygen, and that's attached to another carbon. Keep in mind, in organic chemistry, carbon typically likes to form 4 bonds. It has 4 valence electrons. It needs 4 more to get to 8. Now this carbon is a CH2, and it's attached to another carbon that has 2 oxygens and a hydrogen. Oxygen usually likes to form 2 bonds, and hydrogen can only form 1. So this is the structure. Now once you draw the structure, count the number of sigma bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 sigma bonds. Now to count the pi bonds, keep in mind every double bond has 1. So this has 1, and so the total is 2 pi bonds and 15 sigma bonds. So that's a simple technique in which you can count the number of sigma and pi bonds in a molecule. Now let's spend a few minutes talking about how to determine the hybridization of atoms, which is a common test question that you'll see. So here's some things to know. If the number of groups add up to 1, then the hybridization will be S. And when I mean the number of groups, I mean the number of bonds and the lone pairs. But you want to count a double bond and a triple bond as one group. So single bonds, double bonds, triple bonds are counted as one group, and lone pairs that are not part of any resonance structures are counted as one group. So if you have 2 groups, the hybridization is going to be Sp. 1 plus 1 is 2. If you have 3 groups, it's going to be Sp2 hybridized. 1 plus 2 is 3. 4 groups is going to be Sp3. 5 is going to be D-Sp3. 1 plus 1 plus 3 is 5. And 6 is D2-Sp3. So let's start with some simple molecules. Methane. What is the hybridization of the carbon atom in methane? So this carbon atom has 4 groups attached to it. 1, 2, 3, 4. So therefore, it's going to be Sp3 hybridized. Now what about the hydrogen? The hydrogen only has 1 group attached to it. So the hybridization of hydrogen is simply S. Now let's look at ethylene. What is the hybridization of the carbon atom in ethylene? So focusing on this carbon, how many groups is attached to that carbon? So we have 1, 2, 3 groups. So therefore, it's going to be sp2 hybridized. Now what about acetylene? What's the hybridization at the carbon? So carbon has 1 group, 2 groups. So 2 groups corresponds to sp hybridization. Now what about water? What is the hybridization of the oxygen atom in water? So how many groups does it have? It has 1, 2, 3, 4. So you want to count each lone pair as 1. So therefore the oxygen is sp3 hybridized. Now what about the nitrogen in ammonia? What is the hybridization? So focusing on the nitrogen atom, it's attached to 1, 2, 3, 4 groups. So it's also sp3 hybridized. Here's another example. PCl5, phosphorus pentachloride. What is the hybridization of the central phosphorus atom? So phosphorus in this case is attached to 5 groups. So what is the hybridization for something that's attached to 5 groups? So this is going to be D1S1P3. 1 plus 1 plus 3 is 5. Now what about the hybridization of the chlorine atom? Now keep in mind the chlorine atom has 3 lone pairs. Chlorine wants to have 8 electrons in its outer shell so it can satisfy its octet requirement. So for that chlorine atom, it has 1 group, 3 lone pairs, so it has a total of 4 groups. So it's going to be sp3 hybridized. Now what about the sulfur atom in the center of this molecule? What's the hybridization of sulfur? Now in this case, we can see that sulfur has 6 groups. So the hybridization of sulfur is going to be D2S1P3. You can also say sp3D2. It's the same. Consider this molecule. Now, what is the hybridization of the bond? The bond between the 2 carbon atoms. What is the hybridization of that bond? So far, we talked about how to find the hybridization of atoms. But how do you find the hybridization of the bond? To find the hybridization of the bond, you need to find the hybridization of these 2 carbon atoms. Let's start with the carbon on the left. It has 1, 2, 3 groups. So therefore, the hybridization for that carbon is sp2. Now what about the hybridization of this carbon atom? It's attached to 1, 2, 3, 4 groups. So therefore, the hybridization for that carbon atom is sp3. So we could say that the bond is sp2 sp3 hybridized. Now let's try another example. In this example, find the hybridization of the bond between these 2 carbon atoms. So the carbon on the left is attached to 4 groups. So therefore that carbon is sp3 hybridized. The carbon on the right, this carbon, it's attached to 2 other carbon atoms. So therefore it's sp hybridized. So we could say the bond is sp3 sp hybridized. Now both of these are single bonds. Which single bond is shorter? We know that a triple bond is shorter and stronger than a single bond, and the single bond is longer and weaker than the triple bond. But what if you have 2 single bonds? How do you tell which one is stronger and which one's weaker? Now, when we talked about acetylene, The triple bond had sp hybridization, and the single bond was sp3. So triple bonds have more s character. Bonds with more s character tend to be shorter bonds and also stronger. So which bond has more s character? Is it this bond or this one? Well, we know that sp2 is 33% s and sp3 is 25% s. So if we average 25 and 33, we would get 29% s if you want to quantify it or approximate it. Now on the right, sp3 we know it's 25% s and sp is 50% s. So if you were to average 25 and 50%, we would get a number that's like 37.5% s. So therefore, this bond has more s character, which means that it's shorter and stronger. Plus you can see that it's next to a triple bond. So this triple bond will have an influence on this bond here. So the adjacent triple bond causes this bond to be shorter than this one. So keep that in mind. A bond with more s character is usually shorter and stronger. A bond with more p character is usually weaker and longer. Here's another question for you. What is the hybridization of the nitrogen atom in this structure? Is it S, Sp, Sp2, or Sp3? So looking at this nitrogen atom, it has a lone pair and it's bonded to 3 atoms. So it has 4 groups, and therefore it's Sp3 hybridized. So if you said Sp3, you were correct. Now what about this structure? What is the hybridization of nitrogen in that structure? In terms of functional groups, this is called an amine. And on the right, this is an amide. So is the hybridization of the nitrogen atom, is it still Sp2, Sp3, Sp, S? Which one is it? Is it going to be Sp3 or something else? Now, what if I drew this structure? What if I took the lone pair, form a double bond, and break this double bond? So if I drew a resonance structure, which looks like this. Would you change your answer or would you keep it the same? So what's the hybridization of the nitrogen atom now? Is it Sp2, Sp3, Sp? What is it? Now, when dealing with hybridization, you don't count the lone pairs if it's delocalized, if it's part of a resonance structure. So therefore, you only count this as 1, 2, 3. So it's Sp2 hybridized. If you think about the resonance structure, the lone pair is not there anymore. All you have is 3. So it's Sp2. So when dealing with localized electrons, these are electrons that don't move. They're basically stuck to the atom that they're bonded to. These lone pairs, they're only attached to nitrogen. So when dealing with localized electrons, you count them towards hybridization. When dealing with delocalized electrons, these are electrons that are not stuck to one atom. So this electron could be on the nitrogen atom, or it could be between the carbon and nitrogen atom. So electrons that can move in resonance structures, don't count them towards hybridization. So keep that in mind. Consider these 2 structures. In the first structure, determine the hybridization on the sulfur atom. And in the second structure, determine the hybridization of the oxygen atom. So let's look at the structure on the right. Oxygen has 4 groups, 1, 2, 3, 4. And those lone pairs are localized. You can't draw any resonance structure for this particular molecule. So we need to count the lone pairs towards hybridization. And so since we have 4 groups, it's going to be Sp3 hybridized. Now what about the sulfur atom? One of the lone pairs can move, not both though. This lone pair can move here, causing a double bond to push 2 electrons on that carbon. So this will give us a structure that looks like this. So now the sulfur bears a positive charge and the carbon bears a negative charge. So one of the 2 lone pairs is delocalized. The other one doesn't move. So when counting the hybridization of the sulfur, we have one group here, another group here, and the lone pair that doesn't move, that's stuck on the sulfur. We can't count the other lone pair that can move, that's delocalized. So we have 3 groups, so it's going to be Sp2 hybridized. Now let's go back to the structure of methane. We said that the hybridization of the carbon atom is Sp3 hybridized, and hydrogen simply has an s atomic orbital. Now how can we draw this? We know that S has a spherical shape and P has the shape of a dumbbell. So Sp3 is going to look more like P than it is going to be S, because it's 75% P, 25% S. So it looks more like a P orbital than an S orbital. So when drawn, the sigma bond between carbon and hydrogen is going to look something like this. This is going to be one of the Sp3 hybrid orbitals, and it's going to overlap with the S orbital of a hydrogen atom. Now the overlap of atomic orbitals is known as a sigma bond. So let's draw the rest. Methane has a tetrahedral molecular geometry with a bond angle of 109.5. So as we can see, there are 4 sigma bonds. Every time an Sp3 hybrid orbital overlaps with an S atomic orbital, that's a sigma bond. So all of the hybrid orbitals, I'm going to shade it in red so you can see it. Now what about ethene, also known as ethylene? How can we draw the hybrid orbitals in this molecule? So we said that a double bond has 1 sigma bond and 1 pi bond. The sigma bond is an overlap between 2 Sp2 hybrid orbitals. Now keep in mind, the hybridization is Sp2. So that means that out of the 4 orbitals that carbon has, we're only mixing 3, 1 S and 2 p orbitals. But before we had a total of an S and 3 p orbitals. So we're using only these to make the Sp2 hybrid orbital, which means one of them is unhybridized. The CH bonds will look the same as before. So if you count the number of sigma bonds around the carbon atom, you can see we have 1, 2, 3. And those represent the 3 hybrid orbitals that came from these 3 atomic orbitals. In red, I'm going to highlight all the hybrid orbitals. So the orbitals in red represent the Sp2 hybrid orbitals. Now we need to account for the missing p orbital. That p orbital is unhybridized. So it looks like this. It exists above and below the sigma bond. And remember, a sigma bond is produced due to the overlap of two atomic orbitals. So this here is a sigma bond. And here are the unhybridized p orbitals. The unhybridized p orbitals are used to make the pi bond. So the pi bond exists above and below the sigma bond. So here's the pi bond, here's the sigma bond. So looking at this molecule, we have a total of 5 sigma bonds. 1, 2, 3, 4, 5. And since we have one double bond, we have one pi bond. So in blue we see the pi bond, and in red we can see the sigma bonds. Here's 1, 2, 3, 4, 5 sigma bonds. So make sure you know this for your tests. Whenever you have unhybridized p orbitals, they are used to make pi bonds. And whenever you have an overlap of atomic orbitals, which usually occurs with hybrid orbitals when you're dealing with carbon atoms, those are typically used to make sigma bonds. Now, this is another structure that we need to talk about, and that is the structure of acetylene. So the carbon atom, we know it's sp hybridized, and H just simply has an s atomic orbital. So in the middle, we're going to have an overlap of two sp hybrid orbitals. And then between carbon and hydrogen, we're going to have an overlap between an sp hybrid orbital and an s. So this is sp, this is s. And on the other side, we're also going to have an overlap between s and sp. And then we're going to have two p orbitals, unhybridized p orbitals. So this is the first one. So this is one pi bond that you see here. And then in the middle, we have the sp hybrid orbitals highlighted in red. And this is simply due to a p orbital. P orbitals make pi bonds. Now keep in mind, carbon has one s and 3 p orbitals. We've used an s and a p orbital to make an sp hybrid orbital, which means that there's two unhybridized p orbitals left over. Right now, I've only showed you one, so we need to draw the other one. So I'm going to put this in green. That's the second unhybridized p orbital. A triple bond has two pi bonds. So the first one is in blue, the second one is in green. Now let's say this bond is along the x-axis. The bond in blue would be along the y-axis. Let me put it here. And the bond in green should be along the z-axis. So let me draw this another way. So let's draw the first carbon atom here. And here's going to be the hybrid orbital. And then here's the other carbon atom with its hybrid orbital. And then here's the hydrogen atom with its s orbital. Now I'm going to draw the p orbital right here. I'm going to put the unhybridized p orbital in blue, just like before. So this is one pi bond. Now here's the other p orbital. and I'm going to highlight it in green. And then in red, we have the sp hybrid orbitals. So this is sp, and the one in blue and the one in green are unhybridized p orbitals, and H is an s orbital. So you can see we have two pi bonds, one in blue and one in green. And the one in blue, we could say it's along the y-axis. And let's say this is the x-axis, then this must be in the z-axis. And so you can see everything. And that's acetylene. That's another way to draw it. So that's all I got for this video. Hopefully you found it to be useful. So thanks for watching and have a great day.